I think I will start again. So today we'll talk about the WebKit inter-process communication mechanism, and we will see the latest exploitation method and protection related to this attack surface. So my name is Quentin Meffre. I do vulnerability research and exploitation at Synactive. If you do not know Synactive, we are an offensive security company based in France, and today we are almost 170 ninjas. So last year, Jan Beer from Project Zero released an analysis of an exploit used in the wild, which compromised the GPU process of WebKit. And this exploit is quite interesting in my opinion because it is the first one, it is the first exploit used in the wild which uses the WebKit process to escape the web content sandbox. So I will not detail each steps of this exploit because it is quite complex. And if you want more details, then you should take a look at Jan Beer's blog post. But the main steps of the exploit was first to exploit a vulnerability located in the GPU process to build arbitrary read and write. Then the exploit execute arbitrary NX expression to build a pack bypass, and at the end, the attacker spawn a JavaScript engine into the GPU process to fully compromise this process. So now we will see that Apple hardened each step of this exploit. So first we will take a look at WebKit. So what is WebKit? It is a browser engine developed by Apple, mainly used by Safari, and its first release was in 2005. So basically, WebKit ships everything needed to build a browser, so it has its own JavaScript engine, it has everything needed to render the document object model. It implements lots of web API and many things. Initially, the architecture of WebKit was pretty basic. Initially, WebKit only has one process to do almost everything. So from a security point of view, then this design is very bad because if an attacker is able to compromise this process, then it will have lots of privilege, which is not a good idea. So the developer introduced WebKit 2, which is a multi-process version of WebKit. So now, instead of having only one process, we have one process named the UI process, which is the most privileged process of WebKit, and it communicates directly with a process named web content, and web content is the sensitive process of WebKit. It has less privilege, and it implements every sensitive operation. But even if it had less privilege, then it still had too much privilege. For example, it could communicate with the GPU, or it also had access to few network-related syscalls. And from an attacker point of view, then it's not a good idea to have a surface like that. So now the architecture of WebKit is a little bit more complex. We still have the UI process, which is the most privileged process of WebKit. Web content is also still there, but now the GPU stuff has been moved into a dedicated process named the GPU process. The network stuff has been moved into the network process. And WebKit also implements two daemons named WebPushD and AddAttributionD used to implement web API stuff, and they communicate using XPC with the network process, and all the other WebKit process communicates using the IPC mechanism. And it's also interesting to say that the developers start to develop a new process named the model process, which will be used to do like 3D models or rendering stuff. But today, this process is not enabled by default. So first, web content. As I said, it is the most exposed process of WebKit. It basically implements lots of very sensitive operations like rendering the document object model, executing JavaScript code. It also implements lots of web API. And today, web content has almost no privileges. It has one of the most hardened sandbox profiles of all the iOS system. Web content can use Sandbox extension to extend its sandbox profile, but usually it requires user permission, so from an attacker point of view, then this is not a good deal. And web content has access to some part of the kernel. For example, it can use some syscall, some backdrop. It almost have no access to any user-land services, but it can communicate with each WebKit process. And we will see that this attack surface is quite interesting. So first, web content can communicate with the network process, which is used to do every network-related operation, like loading remote or local resources. And this process also implements web API, for example, the cache API or the shared worker API. It also has a Sandbox profile, which is quite the same than the web content ones, but the network process has access to few network-related syscalls. It also has access to one IO kit, and it can communicate with some user-land services, which make it a little bit more interesting than web content to, for example, compromise the kernel. Web content can also communicate with the GPU process, which is used to do video and graphics processing. Well, basically, this process is the one which communicates with the GPU. And it also implements a web API, for example, the WebGL or the web GPU. And this one is interesting because the exploit used in the wild I talked previously exploit a vulnerability located in the web GPU implementation. And right after this vulnerability has been caught in the wild, then the developers has disabled this attack surface. So today the web GPU is not reachable anymore in this process. The GPU process also does data parsing, like it can manipulate fonts or WebRTC stuff. And it has almost the same Sandbox profile than web content, except then that it can communicate with few IO kits and some user-land services. And to finish, then, the UI process is the most privileged process of WebKit. It does lots of privileged operation. For example, it will display things on the screen. It will interact with the user. It will manage each WebKit process. It will manage the user permission. And this process is very interesting from an attacker point of view because today it doesn't have any specific sandbox except from the system sandbox. So it can access to lots of kernel attack surface and things like that. So before iOS 17.4, each WebKit process were implemented as services, but today there are extensions implemented using the extension kit framework, and the communication between each process is done using MAC messages. So for example, the UI process will start each process. For example, when it starts web content, let's say, it will send its own MAC port to web content, which will initialize itself, and send back its own MAC port to the UI process. And after this operation, both processes will be able to communicate with each other using the MAC ports. WebKit also allows two low privileges processes to communicate with each other. For example, let's say web content wants to talk with the GPU. Then web content will send a request to the UI process, which will forward it to the GPU. The GPU will allocate some MAC ports, send them back to the UI process, which will send them to web content. And thanks to those MAC ports, web content and the GPU can communicate without using the UI process as a proxy. WebKit also allows to filter messages based on the connection type of a process. For example, the UI process has a GPU connection type with the GPU process, which allows it to send privileged messages. For example, it can enable or disable sensitive feature inside the GPU process, while web content only has a GPU connection to web process connection type, which disallows it to send privileged messages to the GPU process. So each message starts with a MAC message header structure, which is followed by a custom structure named custom header, which has 3 fields. The first one is some flags used to describe the message. Then we will have a name, which is an identifier used to identify which handler you want to call into the remote process. And we also have a destination ID used for something else. And WebKit allows to encode lots of data after this header. So for example, WebKit allows you to encode simple data like integer, string, or floating number, as well as more complex data like shared memory or Objective-C object. The Objective-C decoding is based on two well-known Objective-C objects named NSKID Archiver and NSKID Unarchiver. So when WebKits want to share an Objective-C object, then it will use the NSKID Archiver to call the encode with coder method, which will encode the object as a binary playlist data. Then WebKit will send those data to the remote process, which will use the NSKID Unarchiver object to call the initWithCoder method, which will create the object based on the information stored into the binary playlist data. The Objective-C decoding is very powerful. It allows to encode and decode lots of objects, lots of Objective-C objects, and it also supports some complex features. For example, it allows to decode cyclic reference, and historically lots of exploits abuse the Objective-C decoder. And of course, Apple do not really like exploitation methods, so they start implementing protection to kill those exploitation methods. The first one, which is pretty old now, is the NS secure coding. So basically, before the NS secure coding, then the decoded function didn't need to specify the type of the decoded object, which allow an attacker to usually decode arbitrary Objective-C object in a remote process, and this is a very powerful primitive. So to fix this issue, then the developers implement the NS secure coding, which now the decoded function have to specify the decoded object type, and if the decoded object type is different than the specified type, then the decoder will raise an exception. And the NS secure coding still has some interesting feature. For example, it allows to decode subclasses of the specified type. So if someone sets the NS object class into the allowed list, then the attacker will be able to decode arbitrary Objective-C object, because every Objective-C classes inherit from the NS object class. So to fix one more time this issue, then the developers implement the trust restriction, which are applied to each platform binary and each Apple application. And those restrictions will kill lots of exploitation methods. For example, when those restrictions are enabled, the decoder will raise an exception if the NS object class is in the allowed list. Also, the collection classes must explicitly be in the allowed list, so it's a little bit harder to decode classes like NSArray, NSSet, NSDictionary, and things like that. The cyclic reference decoding feature is now disabled with this restriction, and the decoder must use the NS secure coding style. And those restriction also fixes exploitation method related to the NS predicate object, which has been abused a lot of time in the past. So, well, with this new, whoops, what's happened? Oops, sorry. That is wrong. Oh, yes, my bad. Here we are. So, well, with this restriction now, this restriction kills lots of exploitation methods related to the Objective-C decoding. And of course, it was not enough for Apple developers, so they purchased another protection on top of the previous one, which is named the strict mode. It is applied to each WebKit process. It can be enabled using the enable strict secure decoding mode. And this new mode is even more restrictive than the secure coding mode we see previously, because now the decoder can't decode subclasses anymore, and this mode also stops attacker from decoding some sensitive fields of some objects. Well, with all those new protection, Apple breaks lots of exploitation methods related to the Objective-C decoding. And to conclude this part, it's also interesting to say that today in WebKit, very few Objective-C objects can still be decoded. WebKit also has its own Heap allocator named LibPass, which has been designed to be like one of the most performant allocator. And LibPass exposes some API. For example, the most known one is fastmalloc, but we also have the ISOHeap, the GigaCage, and the JIT-Heap, but I will not talk about those API that are not relevant for this talk. So fastmalloc is based on a feature named the thread local cache, which is used for performance reason because using, the thread local cache is used to avoid doing some log stuff when you allocate or deallocate some objects. And almost every WebKit object uses the fastmalloc API to allocate memory. Fastmalloc some kind of sort allocation based on their sizes, and historically this allocator had very few security protection, so attacker could almost usually build interesting primitives to, for example, shape the fastmalloc heap. LibPass has an interesting feature called the probabilistic guard malloc, which is used to try to catch some memory-related bugs in the wild. So sometimes some objects will be allocated with guard pages, and the object will also be segregated. But this feature has a 1 out of 1,000 probability to be enabled, and even when it is enabled, one allocation every 4,000, 5,000 will be guarded. So, this is basically not a security hardening. Instead, this is a feature which tries to catch some memory-related bugs in the wild. But recently, then the developers implement a new feature called T-zone, which today is disabled by default. And T-zone is a new security protection related to the allocator. When the T-zone is enabled, then the information of each allocated object are stored into a macro section named T-zone desks. And when the process starts, it will store each object type into some buckets based on their size, alignment, and a random seed generated by the kernel. And after this operation, when the allocator will have to allocate memory for object, it will use the information stored into some bucket to allocate the object into a dedicated heap. And of course, two objects stored into different buckets will never be allocated into the same heap. And of course, each WebKit process, the content of the buckets is different for each WebKit process, and the contents of the buckets is also different each time WebKit process starts because of the random seed generated by the kernel. Well, with this new security protection, then the developers try to break heap-based exploit reliability. WebKit also sometimes uses the default userland malloc, which historically was very hacker-friendly, but iOS 17 brings a little change related to this allocator. So now each call to malloc has been replaced to a call to malloc type malloc, which uses now a second parameter, which looks like a tag generated by the compiler. And this change might suggest that a new hardened allocator might come into userland, but after doing some tests, malloc type malloc still uses the old implementation, which was insecure. Well, the tag is just never used today. At least into the WebKit process, maybe some more sensitive process might use this new allocator, but I just do not know them. So maybe type malloc might come to userland, or maybe not. So after building some powerful primitive like arbitrary read and write into the targeted process, then the attacker will have to build the pack bypass one more time, which might be different than the one used into the web content process, because web content has its own pack key, so it can be used to sign valid pointers outside of the web content context. And the latest pack bypass targeted the DYLD loader, which in my opinion is a very interesting target because it has lots of optimization, and at runtime it must sign lots of pointers, for example using the DLSIM API or when the loader has to do relocation. Internally then, DYLD uses several sensitive structures. For example, the main structure is the runtime state, which holds a list of each loaded macro into the current process. Those loaded macro are represented using the loader structure, which has a mapped address fields, and these fields points to the virtual address of the macro mapped into the memory. But if an attacker is able to compromise this field, then it can make it point to a fake macro, which has, for example, some fake exported symbols, and when the attacker will call the DLSIM function, then it can make it return arbitrary signed pointers, which is a very powerful primitive. Of course, Apple knows this exploitation method, so they start to protect the memory pages used to hold the DYLD internal structure. So now those structures are protected using the system protection, and DYLD will dynamically switch the protection between read-only and read-write when it needs to do write operation into this structure. So now an attacker can't usually corrupt the structure, but if an attacker is able to call the unprotect syscall using arbitrary parameters, then they will be able to change the page's permission protection, and that's exactly what the operation triangulation did. So to fix this new pack bypass, then the developers now changes the protection used. Instead of using the system protection, then they are using the SPRR hardware mitigation. So now the pages are allocated using special flags named VM flags TPRO, and these flags allow to dynamically change the protection of this memory page. So when DYLD needs to write into those memory pages, then it will set a special value into a system registers. Then it will do the write operation, and at the end of the operation, it will set another special value into the system register to switch the permission between read-write and read-only. So and of course, mprotect can be used to change the page protection, and DYLD is the only one which can change the page protection. So with this new mitigation, then the operation triangulation pack bypass do not work anymore. The GPU exploit used in the wild I talked previously also uses an interesting pack bypass, which is a race condition located in the DLSIM function. So basically, this function will first write the lookup symbol onto the stack. Then it will search this symbol into each loaded macro of the current process, and if it found the lookup symbol, it will return signed pointers. It will just return a signed pointers. But if an attacker is able to corrupt this symbol written into the stack before DYLD searches this symbol, then it will be able to sign arbitrary symbol, which is not a fully packed bypass because they can't sign arbitrary pointers, but it is still a very interesting primitive, which in my opinion allow to do more interesting things. And after building a pack bypass, then the attacker still has to spawn an execution context inside the compromise process. Usually attackers like to do that to pivot into the compromise process and implement the next stages from the new context. As a reminder, on iOS, you can't map RWX pages. Only a few processes like web content and other one can do that, and most of the WebKit processes can't map those pages. So instead, attackers usually spawn a JavaScript engine to have an execution context. So they can do that using the Objective-C API exposed by the JavaScript core. for example, you will have the evaluate script method, which allows to evaluate the given JavaScript code. But you also have object for kid subscript and set object for kid subscript, which allow to get and set JS value inside the JavaScript engine. This can be useful to, for example, corrupt some JS value inside the JavaScript engine and transfer your exploitation primitive to the JavaScript engine. But of course, Apple do not really like this exploitation method. Spawning a JavaScript engine into a process that do not need to execute JavaScript code is indeed not a good idea. So after fixing the GPU process exploit used in the wild, they purchased this commit which says forbid JS execution in the GPU process. So now the attacker can't spawn a JavaScript engine into the GPU process anymore, because when the GPU process will initialize itself, it will trash the JavaScript engine opcode list. So if someone tries to execute JavaScript code, then the JavaScript engine will just crash the process. And also it disables the creation of an object called the VM object, which is a JavaScript engine internal object, and this object is very important to run the JavaScript engine. So if we look at the VM constructor, then we can see that the developer had the checks. So if the VM creation disallowed variable is set, then the current process will crash. But if we look at the GPU function, at the function which initializes the GPU process, well, this function will set up the parameters of the JavaScript engine. We can see that the developers are setting the VM entry disallowed variable, which is used to trash the opcode list, but they are not setting the VM creation disallowed parameters. So basically, the new checks in the VM constructor is just never used today. So an attacker can still bypass this JavaScript engine hardening. All it has to do is to restore the content of the opcode map, but the attacker must have a pack bypass because the opcode map is made of signed function pointers. So the attacker will have to sign one more time those function pointers using powerful primitives. But after restoring this opcode map, then the attacker will be able to use the evaluate script method I talked previously to execute JavaScript code. So escaping the web content sandbox using the WebKit processes looks promising, but at the same time it increases a lot the full chain complexity, because now attacker will have to maintain one more stages to the full chain, which is not a very good idea. DYLD is a good pack bypass target, and at the same time, last year, lots of pack bypass related to DYLD have been killed. And finally, to conclude this talk, I would say that iOS has never had so many user-learned mitigation, but at the same time, last year, attackers were still able to build the full chain from web content. And that's it. Thank you for listening to my talk. If you have questions, I think we have time for one or two questions.